So our final speaker this morning is Klas Markstrom, and he'll be telling us about the number of k matchings in regular bipartite graphs.
And I'll try to make the talk more interesting than my abstract, because when I read it today, it was really very dry. So this is based on joint work with Friedel and Elliot Kopp from University of Illinois in Chicago, and then a follow-up paper with us and Per-Håkan Lundbom from the Royal Institute of Technology in Stockholm. And there will also be some rather important contributions from Leonid Gurevitz mentioned. So I'm not going to tell you a lot of results about where the zeros of graph polynomials are. I'm instead going to show that you can use some of the things that people know about the locations of certain graph polynomials to actually do something else. So I'm going to apply the zeros to doing something. And a matching in a graph is a subset of the edge set, and all the edges in a matching are disjoint. And in physics, this is usually called a monomer-dimer covering, and is sometimes imagined then as a model of some two different types of, well, molecules or something covering some lattice-like graph. And if our graph G has two n vertices, we call a matching with n edges, so that every vertex is part of one of those edges, a perfect matching. So the red edges in this cube would be a perfect matching in the cube. And if M has k edges, we call it a k matching, or a k edge matching. These things have been studied for quite a while, both in graph theory and physics. And if you let bk denote the number of k-edge matchings in a graph G, then we can look at this polynomial, which is just the generating function for the number of matchings. And to make things, well, interesting when you're reading papers and books, there are various ways of writing this generating function. There's also something called the matching polynomial, when you add some alternating signs and you switch the direction of the exponents on x. So, well, it makes some of the algebraic connections nicer. And in a rather large and nice paper by Heilmann and Lieb, they prove that the zeros of these polynomials are real and they are non-positive. And as we just heard, one of the nice corollaries of this is that you actually get this convexity property of the coefficient corresponding to log, well, concavity. And fittingly enough, that's a theorem of Newton. So, oh, and here's where I realize that I will have to use the board because I haven't defined one thing in my slides. So we're going to look here mainly at matchings in bipartite regular graphs. And for bipartite graphs, there's a nice way of representing your graph, which is called something called a bi-adjacency matrix. So if you have a bipartite graph where we have some vertices here, some vertices here, 1, 2, 3, and so on down to n, then we can represent this graph by an n by n matrix where of zeros and ones, where position I j is equal to 1 if vertex I is a neighbor of vertex j on this side. So the vertices 1 to n here, 1 to n here, and aij is 1 if I is a neighbor of j, and 0 otherwise.
That's just one of the corners of the actual adjacency matrix.
Sorry?
It's just the corner block of one of the regular adjacency matrix.
Yes. Yes. And so, and of course, if you have a graph which has weighted edges, for example, then instead of having zeros and 1, you have 0 and whatever your weight might be. And using this representation, we get a nice connection to something called the permanent of a matrix. So the permanent is defined as this sum, which is where sigma is, the outer sum is the sum over all permutations sigma of the numbers 1 to n. So it's exactly defined as the determinant, but you throw out the sign. And the permanent...
So you're considering a bipartite graph with n vertices on the left and n on the right.
Exactly.
Because unless, if they're not equal, there are no perfect matchings.
Right.
There could still be matchings.
Oh yes, oh yes. And there's a way of getting to that.
Right, but you're restricting attention to this n.
At first, yes. So the permanent of A counts the number of weighted perfect matchings in G, where A is the biadjacency matrix of this graph G. And there's also something called the K sub-permanent sum, where you take the sum of the permanents of all matrices B, which are K by K submatrices of A. And then it no longer needs to be, well, A no longer needs to be an n by n matrix. And then those terms which actually correspond to, well, here matchings of any size will come out here. So the K permanent sub counts the number of K edge matchings in this graph. And, well, this is a nice representation of the number of matchings, but unfortunately, to compute the permanent of a matrix in general is a number p hard problem. It's sort of np hard and then a few steps worse. The best known general algorithm for computing permanence is by Riser, and it has running time n times 2 to the n. Of course, the naive algorithm, which just uses this representation, would take time n factorial and a little bit more for doing all the products. And there are some nice special cases. There are graphs where you can turn permanent calculations into calculation of determinants instead by putting suitable signs on things, but that's it's a very restricted class of graphs where you can do this. So the question that we started out to here was, look, given an R regular bipartite graph, should be in there too, on 2 n vertices, what can we say about the number of matchings? And the number of weighted matchings is something that, well, at least for some people, it's of interest in itself, and it's also of interest in certain applications. You can, for example, re-express the partition function of the Ising model in terms of counting weighted perfect matchings. And there are a number of theorems about this. So there's one by Mink and Bregman from the early 70s, I think, which says that the permanent of a matrix A is less than the product of Ri factorial raised to 1 over Ri, where the Ri's are the row sums of the matrix. And as a corollary of that, we can find that the number of perfect matchings in G is less than R factorial to power n over R when R divides n, we get equality, and we get equality exactly for the graph which is a union of a suitable number of complete bipartite graphs with R vertices on each side. And one thing that we conjecture is that this actually extends for not just perfect matchings, but for all sizes of matchings. But taking the disjoint union of copies of KRR really is the extremal graph for the number of matchings of any size. Then you have to say that, okay, R must divide N. What happens when it doesn't? But at least for R equals 2 and 3, we have conjectures what happens for all N. We need to look at some additional graphs. And for R equals 2, a very minor subset of the conjecture, we can actually prove that this works. So this is dealing with 2 regular bipartite graphs. So these are graphs which are just disjoint unions of lots of cycles. And the things with the maximum number of matchings of any size are just disjoint unions of 4 cycles. And this can be proven by doing some work with using the recursive formulas which are available for the matching polynomial. So is this conjecture completely wild? I can just briefly show you this picture, which unfortunately came out very weak plot. The lowest curve here is the conjectured upper bound, and these 2 curves are 2 things which we can prove. This is for R equals 3. So those just come from counting some other classes of subgraphs which include matchings but are easier to deal with. And I just recently found out that there is a preprint available by Galwin, Tepali, and a third co-author, I think, where they claim to have actually proven our upper bound conjecture. But I haven't had time to read the paper yet. But they are people who tend to know what they're doing, so I would say that there's a good chance that they actually have proven our conjecture. So what about lower bounds? And this is where we're going to get. For the upper bounds, we haven't really used anything having to do with zeros or graph polynomials. So for lower bounds, most of the results that people have done have been for Bn, which is the number of perfect matchings. There was the van der Waerden conjecture, which for perfect matchings, it's a bound for the permanent, but I state the implied result for matchings here. Says that the number of perfect matchings is greater than R divided by E to power N. So we are on an R regular graph here. And this was proven in 81 separately by 2 authors, if I remember things right. There's also a result by Shriver, which is more recent, which improved this a bit. You have to think a bit about it, but it is an improvement. And when you're not on perfect matchings, we have something which was known as the Tverberg conjecture, which says that the number of k-edge matchings is greater than this expression. And that was proven by Friedland in 82. And we have 2 conjectures here. First, that in general bk should be greater than this. And it's not immediately obvious that why on earth would you conjecture that. And we actually have a second conjecture, which is about what happens when you take the limit as n goes to infinity, but take the logarithm of these numbers at a fixed relative size. So you want your matching to have a certain density, and then you take the limit as you go to infinity, and we conjecture that you get this. So why on earth would anyone conjecture something like that? It's not something that you just guess out of thin air. So let me tell you why one would end up with a long complicated expression like this. And in order to do that, I will start out with something very particular. Look at k equals 4. These are matchings with 4 edges. Very nice and small things. The number of matchings with 4 edges in a regular bipartite graph can be written as polynomial, which I haven't written out here. It's quite complicated, but it's not that hard to get. You have to do a bit of inclusion, exclusion. Plus number A4 here, which is the number of 4 cycles in the graph. So the number of 4 cycles in this graph is the only thing apart from the number of vertices and the degree which actually affects the number of 4-edge perfect matchings. So, well, this number is at least 0, and it is, you can prove that it is at most the number of 4 cycles in a KRR times n divided by r. So the number of 4 cycles you get when you take the disjunct union of a lot of KRR. And for a random R regular graph, this number A4, the number of 4 cycles, converges in distribution to a Poisson random variable with expectation r minus 1 to power 4 divided by 4. So notice that this doesn't depend on n. So the number of 4 cycles in a random regular graph is not something that depends on the size of the graph asymptotically. Converges to a Poisson variable with fixed expectations.
So this is just random or regular, or this is random or regular bipartite?
A random or regular bipartite, yes. Or you get a different expectation there if you don't add the bipartite condition. So this is a result, I think the bipartite version of the result is by Nicholas Werbold. So once you actually do the calculation, it turns out that conjecture 3, this complicated asymptotic thing, corresponds exactly to, after taking logarithms and dividing by n, this corresponds to the number of k-edge matchings in a random regular graph. You can compute that expectation, it's not that hard to do. And in general, we believe that, okay, yes, there are graphs with smaller number of matchings, but the gap should be bounded on exponential scale, which is what you get when you take logarithms and divide by n. If you look at small graphs, then it turns out that the extremal graphs, so for minimizing the number of matchings, are always cages. So those are the graphs with as large, smallest cycle as possible. And this also, well, very minor result of this slide is that both of these conjectures are true for matchings of size as most 4. But we have a little bit more. There has been some recent work improving many of the different bounds for the number of perfect matchings, and in fact a whole lot of different results, which I will not tell you a lot of details about because I won't have time to do it in an understandable way. And fortunately enough, we have Julius Borsia here, who will give a 1-hour talk about the type of polynomials that I'm about to mention tomorrow. So even if I'm very, very brief, you won't miss too much because you will get a full treatment of the subject tomorrow. So we say that a polynomial with real coefficients is positive hyperbolic if this holds. It should be homogeneous, so all monomials have the same degree, should have degree greater than n. P of x should be greater than 0 when x is greater than 0. So x is assumed to be a real, the values are supposed to be real here. And P of x plus t times u has n real roots in the variable t. So let me view this as a single variable polynomial for all u which are strictly greater than 0 and all real vectors x. And if you also define the capacity of a polynomial like this as the infimum over all positive vectors x, which satisfies the condition that the product of the entries is 1 of the value here, then Leonid Gurwitz has proven a number of different results giving bounds on the behavior of polynomials like this. And one of the results is that if you take the derivative with respect to each of the variables of p evaluated at 0, then this is greater than n factorial over n times the capacity of p. And why is this interesting? Well, it is interesting because the permanent of a matrix can be expressed in exactly this way. So having bounds of this type for positive hyperbolic polynomials gives you bound for the permanent also. And the polynomial that you end up with for the permanent here has a capacity which can be estimated well also. So using these bounds, well, first I won't show the exact expression here now. Gurwitz improved the lower bounds for the permanent to, well, longer and more complicated but better expressions for the value of the permanent of a matrix A. And then Gurwitz and Friedland together proved an extension of the result for the Tweberg conjecture to using this type of methods. And what they could prove was that our asymptotic lower bound conjecture holds for P, so densities of the form R divided by R plus S, where S is 0, 1, 2, and so on. So this tells us that this conjecture is true at a discrete set of points converging down to density 0. So, well, in some ways that's a bit annoying. We know that our conjecture is true in an infinite set of points, but you really would like to know that it's true everywhere. But you can actually fill things in a bit here, just by using the fact that we know that we have real zeros in for this matching generating polynomial, because the fact that the matching generating polynomial has real zeros tells us that we have this, what should be concavity again? This concavity property for bk, which means that, okay, the bk sequence has to be concave. So if we just connect all these points so we know that the conjecture is true by a line, then that's also a valid bound. And if you do that, you get something that, well, the upper curve is the conjecture and the lower curve is what you get when you connect the point where we know that the conjecture holds up with lines. And, well, for high densities there is a noticeable gap. For low densities you can't really tell that there are two curves here. But you can do better. And that's, again, thanks to, fittingly enough, the person who has named this particular institute. Because Newton didn't just tell you that you had concavity. You, in fact, have concavity after dividing by binomial coefficients. This is the simplest case of a whole collection of inequalities called the Newton inequalities. for polynomials with real zeros.
Not positive here is irrelevant. You can drop it.
Yes, that's true. I think I ended up in non-positive areas because it happens to be true for our particular polynomial. Yes. So, and this also tells you, if you look at the full statement theorem, this also tells you that you only have identity here when you actually use, when you have the standard binomial polynomial. For all other polynomials, these inequalities are sharp, these are sharp inequalities. So this tells us that, okay, instead of just connecting things up by a line, we could actually first subtract what we get when we take logarithms of the binomial coefficients, then connect things up by a line and push things up again. So if we do this, well, we get an improved bound, and you end up with something like that. Now it's unfortunately quite hard to see, so this is the line, this is what you get when you add things up, and this outer very weak curve is the conjecture. So no, we haven't proven the conjecture yet, but we know that at least it's not horribly false. And this is for a very, I think this particular plot is for r equals 3, and they do get better and better for higher values of r. You have the largest gaps for small r. And in fact, we have one more improvement on this when we actually use the convexity a little bit better to just, okay, connect the points up in an even better way. But, well, the nice thing here was that, okay, we couldn't prove the conjecture in general, but just thanks to knowing something about the location of the zeros, we could actually get a reasonably good bound for the result, even at the points where the nice hyperbolic polynomial techniques didn't apply. So I think I will finish there.
Questions? Can we thank class again?